Okay, so it's a real pleasure to have Adam, one of the co-organizers of the semester, giving the last formal talk. There'll be some lightning talks after this. So Adam's going to tell us about the energy and uncertainty, part 2.
Thanks. So you had a lunch break, but hopefully you remember what Eilyan talked about in the first part of the talk. We actually spent some time thinking when we were deciding what to do for this tutorial, how to organize it, and we settled on what you've been experiencing, which is this, where we gave you 10 or 15 minutes of a high-level overview of how the grid works, how the electricity markets and stuff filled in, and then what we're trying to do with the rest of it is identify basically 4 themes of problems that are hopefully appealing to segments of you that I think you can approach pretty cleanly without a lot of background in electricity markets. And if you see algorithmic challenges in these domains that are interesting to you, that's the goal. And then we're both here for a lot of the term, and we have a lot of students that are here during the term. And so we can help with the details of energy throughout the way. But this is hopefully enough to get you intrigued that there are neat algorithmic problems in the space of energy. And then we can discuss them further as the things goes on. And so Eilyan talked about chance-constrained optimization and online learning as 2 places. And he gave examples of where these are used in electricity and smart grid and these sorts of things today. There's lots of other places where these problems come up as well that he didn't talk about. So if you're interested in these areas, you definitely should follow up with him and me and our students. And I was tasked with talking a little bit about markets. And really, since we already had an hour or more this morning on algorithmic mechanism design, I figured I wouldn't rehash a lot of those. A lot of those ideas are very prominent in electricity markets. And so what I figured I'd talk about a little bit instead is the challenges that are of a little bit more of an algorithmic nature and the things that come specifically because of features of smart grid and electricity grids, something that's a little special to this domain. And so the 2 that I'll focus on are selling tomorrow's energy today, which is basically a news vendor problem, and why news vendor problems come up so frequently in electricity markets and the research there. And then the second one is really on these Kirchhoff's laws, these network constraints, and how they make markets challenging. And I just want to give a flavor of each of them and connect them to models and problems that I'm hoping you're familiar with or at least have heard of before, so that you can have a nice entry point into this domain if you want to work on these problems. And really, the goal of the whole, the 2 hours that we're giving you is to, identify that uncertainty is really the problem for energy today. And so it's nice to focus on it during a, program on algorithms and uncertainty. And that there's a lot of models at this point that can be attacked without being a power systems expert, where you can have an impact on the community with a one-hop step. And I hope that we can have some of those one-hop impacts over the term. Okay, so that's the intro. And now for the first one, we're going to do this, tomorrow's energy today theme. And so this is really just news vendor problems. And we already saw 2 news vendor problems in Eilyan's talk. And so just forget about energy for a second. And let me remind you what a news vendor problem is. So this is 1800s, I think, 1888, if am I remembering correctly, is the first time somebody talked about news vendor problems. So it's an old problem. And it's basically the task of you're going to go sell newspapers out on the street tomorrow morning, but you have to, buy them now. And so you have to figure out how many you're going to buy today when you're going to sell them tomorrow. And so to do that, you have to estimate the demand. You estimate how many you're going to need to sell. You get that D hat. You purchase some amount based on that estimate. Tomorrow, the demand is realized, and you sell. If you overestimate, I guess, sorry, this should be a hat. If your D hat, or I guess if your realized demand is more than X, then you lose some money, right? So you didn't have enough available to sell to them, so you left some money on the table. And if your what you purchase is bigger than the realized demand, then you're wasting inventory. Right? So both are bad, and you try to be as close to the accurate thing as possible. And the question is how you do this. So that's news vendor problem, and uncertainty is really the difference between your estimate and the realization. And of course, it's called news vendor, but really it applies anywhere where there's some sort of perishable good. And energy is a very perishable good. If you don't have large-scale storage, then what you produce today you can't save for tomorrow. You have to use it now, and if there's not a demand for it today, it's wasted. You burn it in an air conditioner out in the desert, something like that. And so how does this come up today? Well, this is, you heard a lot about how the grid works from Eilyan. This is my simple, 2-slide reminder in a cartoon form. So if for an algorithms person, you can really sort of think of it as really the key thing that's going on in the grid is that every time you're balancing the demand, the load with the generation, and you just have to make sure these match. And the way you do that is you predict load, and you have low uncertainty. This is my version of Eilyan's plot showing how good we can predict load. So this is 3 lines. The purple is the day ahead. This is 4 hour ahead, and this is the realization. And so you can see you can really predict demand very accurately. And once you have the prediction of the load, you turn on generation to match it. The things that take a long time to turn on, you turn on way ahead of time. The things that you can turn on more quickly, you wait until the last minute to turn them on, and you only turn them on when you need them. And that's basically it. And you can do this so accurately that you can get away with controlling generation with markets. Right? So if you couldn't predict as accurately, you'd have to really depend on real-time control, and you wouldn't be able to integrate markets as well. But because you can do this a day ahead, you can really run markets at a day ahead and then again at 15 minutes ahead, and let the markets clear, and then only deal with the remnants in the control. So the economist kind of governs the system for most of the time basically up until the last few minutes, and then the engineer, the control theorist, takes over and does the fine-grained tuning. So that's how it works. And the markets, you can think of a caricature like this, where you have your real time a couple minutes ahead of time, 5 to 15, your day ahead market, and your long-term market. And these are really markets. These are long-term contracts. These are signing a contract 10 years ahead, saying all of my wind goes to you for the next 10 years. These sorts of things. And really, most of this, this is most of the energy. So this is, maybe you can correct me, somewhere around 80% or more of the energy purchased, I think, is in these long-term contracts, and this is more like 10 to 20% of the amount. But this is still a big amount that comes in these markets.
What's the ratio between these?
Between these, actually, I don't know. Eilyan, do you know? Sorry? The ratio between real time and day ahead, how much electricity is contracted here versus here? Maybe 5 to 1? Yeah.
Aside from long-term bilateral contracts, any residual.
Yeah. I think it's kind of like 8 to 10 to 1, and then 8 to 10 to 1 sort of recursively down, but I'm not completely sure.
Those long-term contracts have to be integrated into these.
Yeah. Okay, so that's kind of how it's always worked. What's the change today? Well, Eilyan talked about it. Basically, the load, well, for now we still have low uncertainty because DR is a future thing for the most part. Demand response is something that's coming. It's not really here yet. It might bring some uncertainty here, but right now this is still pretty low uncertainty. But the big change is once you have solar and wind, you can't control these. You can't predict them. It's a lot of uncertainty on that side. And that means you have to change the model. You have to get some control here so that you can react on this side as well as this side. But it means you have to change things. And really, the changes happen because of volatility and uncertainty coming into the markets. That's where the inefficiency comes from. And you have to deal with it in the control too, but the changes come from it coming into the markets. And how does this manifest? Basically, if you have wind, actually, and this is already happening, so there's lots of wind long-term contracts. I mean, Edison, Google is in some sense an energy generator nowadays. They really have large portfolios of wind power all over the US that play in these markets and look at long-term contracts. And then there are programs that the wind can play in real-time markets as well. And what happens here is, if the wind is blowing when you don't expect it or is not blowing when you expect it to, that leads to price shocks. And so you get huge variability in prices as a result of the uncertainty in wind and solar. And basically, these variability in prices can be countered a little bit if you just have extra generation called reserves on as backup. And we do have those. And so you can think of a future where to fight variability, you keep larger and larger reserves. But that counters the point of, why are you having renewables if you have to keep a coal plant on in the background to make up for the fact that the wind might not blow? So that counters the sustainability gains. And the huge price variability also is dangerous for the sustainability gains because things like nuclear and that are slow to react get forced out of the market if there's these huge price variability. And these aren't just academic things. I like citing news articles, and so basically this volatility can be enormous. You can have prices that are positive and negative. The prices can go extremely negative in these markets, and they do frequently, which is something that's a little unusual when you think of other markets. So it's exactly what you think. So if I'm not, rather than me paying you for the energy, I'm paying you to not give me energy.
You get paid to consume.
You get paid to consume, right? So you get paid to provide negative demand. Yeah. And so, this happens all the time, all over in the U.S. and Europe. And, the big picture result is a little bit pessimistic, actually. So Germany is maybe one of the biggest investors in these sorts of changes in renewables, and they've made some mistakes in the way they align their market. Most people would say, and they're what, 4 or 5 years now into their big initiative, and greenhouse gases, their emissions have gone up, not down, even though they're at significant penetration of sustainability. And there's a lot of factors that led to this. For example, reducing nuclear, but a lot of this is as a result of basically countering the uncertainty of renewables with reserves that are very dirty. And so you end up with a situation where you need to think about how to redesign the markets to avoid these factors. That's kind of the high level. And Eilyan talked about this in the case of the real time and the dispatch and risk uncertainty and how you price DR and all of those approaches for countering this in the first part of the talk. And my goal here is going to be to more talk about how you deal with procurement across this time scale and how the network impacts the inefficiency of these. And so the first one about selling tomorrow's energy today is really about looking at what happens so you contract for long-term wind, how does that impact what goes on in these markets? And the second piece will be about how the network constraints play and create inefficiencies and uncertainties in here. Okay, so the first question is really, how do renewables impact this market structure, and what could they do? Well, the natural things are, we know we're going to have these sequence of multi-timescale markets. Well, should we add more? Should the uncertainty mean that we add more markets? Should we add markets closer to real time so that we have more certainty when these markets clear? All of these sorts of things are very natural, intuitive suggestions. And so you could move this around based on how your predictions look. You could move it closer. You could add new markets. Maybe we should have a 4-hour market and a 2-hour market and a 1-hour market. And could we get more efficiency by going to a model like this? These are the questions that really drive a lot of the field. And so to give a flavor of how those work, I figure I'll just show you one simple version of a way to approach those questions. And this will in turn show you why news vendor is so useful in these domains. So the first step maybe is to think about, suppose we have a situation like this, and we have wind coming in the long term. How does that affect procurement in the other markets? So if you're a utility and your job is to make sure supply matches demand, and there are wind contracts that you have to take because you're mandated by the legislature to improve sustainability, what does that impact? How do the long-term contracts impact what happens in these other markets? And so imagine a picture like this. And so you have prices for the purposes of this talk. The prices are going to all be exogenous and random, but lots of good research is going to making them exogenous and to actually model the market dynamics here, but I'll keep it simple for the talk. And so think of prices coming in these long markets. In these markets, of course, the prices are going to be more expensive on average at real time than at long term. Contracting in advance is cheaper. And so you have something like this, but the volatility of the prices should be going up as you get closer to real time. Because this is when the realizations of the wind happen. And so we'll look at a model where this maybe is a constant. This is something random where its mean is bigger than the long-term price. This is something random where its mean conditional on the intermediate price is bigger than the long-term, or is bigger than the intermediate price. And then you're going to purchase some quantities. These are what you're actually purchasing or procuring from the markets. That's your goal. And you're going to purchase them, but there's uncertainty, right? You're purchasing them based on some prediction of what's going to happen in the wind. And so at the long time frame, think of this as really long. This is a year or so in advance. So this is basically an average case prediction. This is kind of like the mean. And then going forward, you're going to have some error in your predictions, and your predictions are going to get better. So if you're familiar with it, think of this as like a martingale forecasting model. It's a little bit more general and simple the way I've written it down, but basically you have some martingale that you're predicting, and you have some improvement in your error from the estimates at each stage until finally you see the realization. And so then what's your goal? Your goal is to procure enough generation, so at the 3 different stages, so that along with wind, you have enough to get demand. And if I wanted to make this more complicated and realistic, I could have a penalty cost for having extra energy and disposing of it and these sorts of things, but this is the simple version. So that's the setup, and now I have to give you an objective, so minimize cost, right? So you want to meet all demand and minimize cost. Yeah?
You're procuring wind in all the stages, right? I mean, it's...
So the wind, think of the wind as something that you've bought it ahead of time. You have to take it. But you don't know what it will be until here. And think of the procurements or of the conventional stuff that you're trying to get to make sure that you have enough along with the wind. So you've bought, yeah. So you've bought the wind already in advance. This is from Google because Google wanted to improve their image and say they were net zero, and so they sold you a lot of wind. And then you're having to buy nuclear and coal and gas to get enough.
Long-term
contract. So think of this as a price external to what you're trying to optimize, because you've already, these are sunk costs, and then you're trying to minimize the cost of procuring the rest of the generation. That's what this objective that I'm right there.
When in real time, can you predict what the wind generation will be in an hour?
So these real-time market, think of it as 5 minutes ahead, and for the purposes of this model, I'm capturing it as exact, but I could make that random too if we wanted. This is really the simplest place where I have three levels, and I can show it to you. So all of these variations are very interesting. Some of them there are papers on, not all of them. There's a lot of open questions about how these affect the policies that result. Okay, and so as I've framed it, it should be obvious that this is, a 3-stage news vendor type problem with martingale forecast model as the look ahead, and so you can just derive a policy. And so this is what the form of the policy looks like. I'll hide this for the moment, so you can focus on the structure first. And so basically, you get a structure where, in the long term, you're buying the excess that you think you'll need, plus an extra reserve quantity, which makes sense. In the intermediate, you do the same thing. You buy the extra. Now you know what you've bought. You have your new forecast. So this is, again, the extra that you think you'll need. If you're not already covered, if that's positive, then you do it, and you keep a little extra reserve to keep yourself safe, because you know it's going to be more expensive to buy it later if you miss it. And then here you clear things out. So it's got a very natural structure. You keep a reserve at every level above what you think you'll need at the moment, and the question is how big those reserves are. Yeah?
Maybe this is obvious, but I don't see why on expectation it should be more expensive later.
So it's not obvious, right? So it could be, this is something that's a function of the type of generators that play in the markets. So think of these as more likely to be things like nuclear with low marginal cost, and these to be things that are more likely to have high marginal cost. This does change over time, though. Natural gas becoming more popular gives you things that are cheaper up here than they used to be. Yeah. Okay. And so that's the structure. And then the math is basically to figure out what these reserves should be. This should look really familiar to anyone who has studied a news vendor problem before. This is just the critical fractile. And so that's exactly like what you would get in a standard news vendor problem, except the notation is a little different, basically. When you go to that second level reserve, things already start to get very complicated. So I can't write down an explicit nice form for it, although I can write an implicit function for it. And so that's kind of it, and it's a little bit of a pain to work with already at this point. And if we're going to start to ask questions about how many markets are optimal or where should we place markets, we have to have a better feeling about what this form looks like to be able to answer those questions mathematically. And so what this is now getting into some of the work that Eilyan and me and others have done in recent years is to say, let's look at how we can scale this. And if we can come up with a scaling parameterization, maybe in the scalings we can start to see structure that you can't see as well in the form. And so this is also a very queuing-like thing to do. So a lot of the queuing people here are used to this kind of argument. Yeah?
So far, the sequential procurement based on increasing information, is this different than, distinct from risk-limiting dispatch? No.
I just didn't use the terminology. Okay, and so now to do the scaling, one way to do this is just to think of the scale as being kind of the number of wind farms, and so we'll think of that coming out here, and the scaling is going to be on the estimates here. And so think of there being a baseline average output for one, and your long-term estimate is basically the average. So we scale up by the number and we multiply by the average. So this is like a law of large numbers kind of prediction. And then as you get better, you're getting better. Yeah, so we're going to scale up again. So there's the epsilon 1 for the intermediate level, and we're going to pay kind of, if theta was 1/2 and everything was independent, this would be like a central limit theorem type scaling for your estimates. But I like to think about heavy tails and allow things to be a little bit more variable. And so if you think about more a generalized central limit theorem type scaling, this could be anything between 1 or 0 or whatever, depending on the correlation structure or the heaviness of the tails in your estimates and things like that. And so you can really have a kind of more arbitrary polynomial form, and that gives us some interesting things to think about. But I guess the easiest way to think about it is just the degree of correlation. If everything's correlated, then this would be 1. If everything's uncorrelated, then it would be 1/2. And so on. So the nice thing about this scaling is it gives kind of what in sort of OR or management science you say, like, management science as a journal always looks for managerial level insights. And this is like one of those equations that fits as a managerial level insight, right? So you don't have to have much math to understand it. You get that your expected procurement is what you have to buy. This is what you would have to buy to make demand match supply, plus a little extra. And that little extra has a very clean form where there's some parameter that depends on markets and prices and is very complicated, but it's completely separate from the thing that depends on how wind aggregates and how you can predict it. So you get this nice separation. And this separation leads to basically, if you want to understand the role of the markets, all you have to do is analyze this term, the delta term. And I won't expand it out because it is a little ugly, but then you can really just focus in on that and you can understand the structure very simply. And everything, I just want to really make the point. Everything that I presented here is a really simplistic model. There's more general stuff here. There's lots of open questions, but there are also more general results. And just 3, since people are here for these, Eilyan and Praveen have a really nice paper on this, which motivated our work, actually. And they take this to much more than 3 markets. And then, this is the paper that I summarize here. And then there's some other works as well from our groups. But there's lots of open questions about how to embed, penalty costs, more markets, and no one has really answered the question of how many markets are optimal. And so if we get, the motivating questions are really where should the markets be placed, how many markets should there be, and I would characterize those as open with any sort of general degree of models.
Is there an intuition for why more markets just wouldn't always be better?
So that's going to be my next few slides, just to motivate you to say that this is an interesting question. So already in this simple model, I can maybe intrigue you a little bit here. So should they move more close to real time? That's the question. The answer here, I'll just say no, and you can come ask me afterwards for why, because it's a little bit complicated. But it turns out that this delta term, it's very easy to see that it's kind of independent of the placement of the market. And so moving markets, assuming that you're already in a near optimal state, won't help you, which is a little bit counterintuitive. I thought it was going to be very clear that it moved closer. But I think the even more intriguing thing is, should markets be added?
Does that also prevent things like having negative costs for consuming electricity?
That's a network effect. That's a network effect, yeah. So I'll get to that in the second part. Okay, so the next one is, how many markets? And here, there's no general answer to this, but I can give you like a simple caricature of 2 versus 3 to show you that the problem is interesting and warrants more study, basically. So the first order thing is, what happens to the cost of procurement? So if I only care about how much the utility pays to get this generation, having more markets is certainly better, right? Because I can just purchase exactly the same thing in the more market case as I did in the fewer market case, and I could do something else that would be better. So it's directly better. So the cost will go down. But the more interesting thing from the societal perspective is, are you going to use less conventional generation because you have more markets? Are you going to buy less coal or less gas because you have more markets? And that's what you want. You want the total amount of procurement to go down. And that's where, a little bit surprisingly, basically it can go either direction. And the nice thing, so if whoever heard my talk on on Tuesday on the queuing stuff, we had this conspiracy versus catastrophe characterization of heavy versus light tails. The same sort of intuition and the same sort of analysis and insights apply here. And it's a little bit more general, actually. But first let me explain what happens. So as a concrete example, think of long-term price 6, 10 here. This will be somewhere in between, and I'll plot for you what happens. So if the errors are Gaussian, so a place where conspiracies happen, a light tail place, then everything is as you would expect. With 2 markets, there's going to be some cost. It's constant because we don't have an intermediate market. With 3 markets, everything's nice and monotone, and it's always better. The procurement is always less. So this is kind of what you'd expect going in, or at least what I expected going in. 3 markets are always better. And we can actually say something concrete about when this happens. It basically happens if this condition is satisfied. And this is, if you look at this is density. This is cumulative distribution function of the error term. And basically, this is the left tail. And so this is increasing hazard rate for the left tail. Increasing hazard rate of the CDF and increasing hazard rate of the PDF. Okay. So there's some structure there, and that'll come up because the other half also will depend on the hazard rates, and so I'll say a little bit more about it. On the other hand, if we go to something heavy-tailed, say a Weibel, a heavy-tailed Weibel, you see a stranger behavior. You see that sort of if the intermediate price is large enough, close enough to the real-time price, you get this hump where you procure more despite there being an extra market. And when does this happen? Well, it again depends on the hazard rates, but at least what we can prove, and neither of these are necessary and sufficient, these are just the best we can show right now, is that long-tailed is important. And here, I like heavy-tailed, so I'm going to take a diversion. Long-tailed is a class of heavy-tailed distributions. I'll go into lecture mode. And it's nice because when I talked to you on Tuesday about conspiracies and catastrophes, this had to do with this one particular property and this one particular class of sub-exponential distributions. Long-tailed distributions, they also satisfy catastrophe principles, but it's a more general class, and it's a class that's defined in terms of behaviors of the residual life. Which is also something that Nikhil taught you about on Tuesday. And so we'll do a little bit diversion about residual life and how they relate to heavy tails and light tails. And residual life is really the key to those 2 results that I just showed you. That distribution.
So what's the difference between long tail and heavy tail?
I'll get to it. So residual life, it's going to be defined in terms of the asymptotic residual life. And so residual life is this remaining waiting time. So Nikhil described it in terms of waiting for a bus stop, and would you expect to wait longer or shorter? So I'll describe it in a similar way. So just to get us in the mood, what happens to our expected remaining waiting time as we wait for various things? If we wait for a table at a restaurant, for a bus, for a response to an email, my students can understand this one from me. So the table for restaurant, it's pretty nice in behavior, right? So you get there, they're going to give you an expected wait time. Basically, people will leave. You'll see people leave. Your expected remaining time, it's always decreasing. Every time you see somebody leave, your expected remaining waiting time will decrease, and so on. There's not weird jumps. There's not weird monotonicity that happens, right? So it's expecting and decreasing. For a bus, there's this period where it's like that. Until the scheduled time, your expected remaining waiting time is decreasing. But after the scheduled time the bus was supposed to get there, maybe something happened, right? Maybe the bus broke down. For a little while, maybe your expected waiting time is still decreasing. But after a while, it's likely that something happened and the bus just isn't going to come. And so then your expected waiting time starts to increase again. And then the email is an extreme version of this. Like for me, if you email me, you'll get a response within like the next couple hours, or you won't get a response, right? Or there's this sort of extreme where you either respond to it right away or it takes forever to respond, right? And so there's this kind of very increasing mean residual life sense to email compared to decreasing mean residual life sense for this. And this effect of the residual life distribution really connects with heavy tails and light tails. And so concretely and mathematically, this is the residual life distribution. So this is the probability that the residual life, the distribution of waiting time given that you've already waited x is this. So the likelihood that you're going to have to wait t seconds or longer, given that you've already waited x seconds, in terms of I use the bars for the tail, so this is the probability that your job or your waiting time was going to be larger than this. This is the probability that your waiting time was larger than this. So this is probability given this. So that's kind of by definition. You can write that down. And so you can see this if exponential, it's memoryless, as you'd expect. This ends up not depending on x. So the key here is that the time, the distribution of the remaining time given you've already weighted x is independent of x because it's always the same as your initial probability. For something heavy-tailed like a Pareto, it depends heavily on x, and it's going to be increasing in x. Okay. But this is a little bit complex to think about. And so most of the time when you start thinking about residual lives, you don't think about the whole distribution. You think of some statistic of it. And so these are the things that you've probably actually heard of, even if you're not in this area. And so the mean residual life and the hazard rate are the summaries that most of the time people talk about with these. And so the mean is just the mean of it. So that's it in math. And the hazard rate is the PDF over the tail. And we saw this comes up as the virtual valuation function in Meyerson. It comes up all over the place. And for the most part, and people often think this is a one-to-one, but for the most part, heavy-tailed distributions tend to be decreasing hazard rate, increasing mean residual life, and light-tailed distributions tend to be the opposite. And so these are properties that people tend to associate with each of them. It's not true that light-tailed distributions are always increasing hazard rate and vice versa. So there are lots of heavy-tailed distributions that have an increasing, or that are not all heavy-tailed distributions are monotonic in this way, and some light-tailed distributions can have the opposite behavior. And so this alone isn't the way that you characterize this stuff. And this comes up, right? The bus wasn't monotonic, the email isn't monotonic, but they're eventually increasing, and so they have the heavy tail probably at the end of the day. And so this leads to the way that you actually work with this stuff in proofs about heavy-tailed distributions is the class of long-tailed distributions. And it's really just looking at the limiting behavior of the residual life distribution. So this was that residual life distribution. This was it expressed out with the conditional explicitly. And you basically just argue that eventually, if you've waited long enough, if x is getting large, then you're going to have to wait an infinite amount. So you can see the relationship of this to the catastrophe principle that I was talking about on Tuesday, right? There's some really big catastrophe that could happen, but it's a little weaker than that. It's not the explicit characterization in terms of the sum. It just says if something is going wrong, then it's going to go really, really, really wrong. That's kind of the way to interpret this. And the name long-tailed comes from you're stretching out the tail with the t, right? So it's long because x plus t versus x, and the ratio is 1. And so like the last one, this is a subclass of heavy-tailed distributions. It includes everything that you've heard of, but there are weird cases that are not long-tailed. And it includes sub-exponential. So not every distribution here satisfies the catastrophe principle, but all the common ones do. Okay, so that's kind of my thing. And it's this that's really the key factor for the two theorems that I showed you before. It's really this notion of if something is going to go wrong, it's going to go really, really, really wrong. And if your error predictions satisfy that, then it can lead to the really inefficient behavior in the markets. Okay, so that's that. And so summarizing the news vendor thing, again, there's this huge impact of heavy-tailed versus light-tailed prediction errors on the efficiency of markets and how you should design the market structure. And we don't understand it very well. Everything I showed you is for 2 versus 3. There's nothing that takes it beyond that. Yeah.
This might be a silly question, but in practice, the amount of power you can produce by a wind farm, these things all have bounded support. So how would that affect this story?
Yeah, no, that's true. And so these are theorems, with a bound, this is the extreme situation. I can come up with bounded distributions that will satisfy both of these, but then you're playing with little weird parameters, and it's not so fun, right? So this kind of expresses the intuition, I think, that will hold more generally. And it's kind of, just to hit on that point, in terms of practical impact of this, one of the sort of funny things is, Weibull versus Gaussian are the two most common modeling assumptions made for prediction errors of wind these days. And they have completely different behavior in terms of what you should do in terms of adding a market for 2 versus 3. And we don't know which one is a better model. We don't know which one is real, all these sorts of things. So in some sense, this is highlighting that there's a lot of uncertainty in how to approach these problems. Okay, and so this was one example I just want to highlight before going on. There's lots of other things. We talked about wind in the long term. Wind is really in the short term, and Eilyan talked about this a lot. And so there's lots of interesting questions about basically where wind comes into these market problems and basically how you deal with uncertainty in multi-stage markets. Okay, so that was the multi-stage market. That's one thing that makes electricity markets really special and different from the sort of typical algorithmic mechanisms design work that we do in AGT and theory. The other is the network, is Kirchhoff's laws. And so that's what I want to highlight in the second part. And again, the things and the insights here are completely, they're applied and useful in energy, but they're really interesting well beyond energy. And so really everything that I'll say, even though I'll couch it in terms of energy, is about competition in networked markets. And I think this is something that's really important for AGT as a field to do, beyond just its application in energy. So in the real world, competition isn't in a single well-defined market. There's not an equilibrium up price. There's lots of different markets that interrelate in different ways. And firms compete across a bunch of markets. And we don't have a very good understanding of the consequences of constraints and connections between markets. So you can think of this, all the utilities satisfy this. Here's my electricity grid, but gas pipelines, airline routes. You can think of platforms in general, Uber, Airbnb, DoubleClick, ad auctions, ad exchanges. All of these are, again, networked competition. There's sub-markets for different types of users in ad auctions, and these sub-markets interact. And firms are deciding which ones to compete in and how to divide up their allocations across these. And the exchanges are really fundamental to how these things work, and we don't understand them very well. And so the caricature here is, in some sense, you have firms, you have markets, and the firms can compete in some of the markets and not in others. And this matching is sort of fundamental to the competition and the prices that will emerge and the efficiency of the marketplace as a whole. And how does this work? And this matching is complicated. So if you think of an Uber or a platform type design, you're optimizing that matching. If you think of a utility sort of framework like electricity markets, this matching is kind of given to you, and you're trying to do the best you can given the constraints that matching provides, or at least the high-level matching provides. And given that it's complicated, that's why platforms tend to exert some control, and that's why we have the ISO, the Independent System Operator, in electricity markets, where it's governing that matching. There's some market entity that's centralized that does this matching and takes the bids or productions or whatever from the firms and allocates them across markets and determine prices and these sorts of things. So yeah, there's lots of examples of those. And so that's the the broad picture story in electricity. I guess before I go to electricity, I think one of the big questions in this sort of market is efficiency, clearing, equilibrium of that, but also market power. And market power is really a big issue here, because once you have a single, in some sense, market power in a single market is easy. You make sure there's enough competition, there's enough firms, they're not colluding, you're okay. In here, what is enough competition? You can have a firm that is well positioned in the network but produces a tiny, tiny amount that still has monopoly power. And we don't have any sense right now of how to measure really market power and monopoly and check for those things in general markets, in network market cases. So this is really, hidden monopolies are common, and I'll demonstrate that in electricity markets now. So this was our electricity market case, and the caricature I gave before was just generation equal load. To make it one step more complicated, it's not really generation. There's not a single market where generation matches load. There's a network. And so you have generators on the network. You have loads on the network. The network has edges that constrain flow. And you need to make sure generation matches load at every point in the network. Or in some sense, the network is stable so that the generation matches load given the network constraints. So how does that happen? Well, you have your market maker, your ISO, and they basically take the loads and they take bids from the generators. And these bids in electricity markets are supply functions. So you bid, I can supply this much at this cost. And you give usually a parameterized version of that supply function curve. That's your input into the mechanism. This is basically your mechanism design question. How do you design the ISO? And then you clear that subject to network constraints. And the network constraints, I'll do what Eilyan did, and we'll just think of these as linear constraints as capturing Kirchhoff's law. So you don't have to care what Kirchhoff's law are, just there's some linear constraints here. So as a toy example to show why this is hard and why this leads to problems. So think of just 3 nodes. We have a load here. We have 2 generators. They're symmetric. They are uncapacitated. So there's a load of 6 here. You have 2 generators here that could each produce unbounded capacity if you ask them to. And yet, there's a monopoly here. Both of them have a monopoly power. And the reason why is, so suppose we produce 3 here. Well, we'll take all the lines to be equal impedance, which means that basically, for every 1 you send here, a half goes this way. So if you were going to send 3 to this to satisfy load there, it would have to go like this through the network. And so that's all fine and dandy. But we have this capacity 1 here, which means that that's actually the most that this generator can send. So how do you get 6? Well, you have to depend on the other guy sending 3 as well. And so they'll get their 2 to 1 here. These cancel out. Now you're at 0 in this line. So you could satisfy way more than 6, but this will already get you to 6. But now what happens here? If either of these are strategic, they realize, hey, I can bid unboundedly large because no matter what I bid, you have to use me. And so both of these can drive the price up arbitrarily. You look confused.
I've never understood why Kirchhoff's laws bind in the way they do. Like, why can't you just break the line, have some kind of switching?
Have a switch so that you just turn off that line.
Yeah.
So that could be a response to this simple example. That won't help you in general. So this is toy.
But you can't do that.
But you can't, right? You can't just turn off a line either. Right?
You can, but that would have implications in terms of the prices that are set at other nodes, and that may not be acceptable to all stakeholders or participants.
It just seems like a degree of design freedom rather than being stuck with a particular network structure. You could break edges here and there if that turned out to matter.
No, so the utilities are looking into this to some extent. They're looking into flexibly adjusting the configuration of the network for reliability reasons for lots of things. But it's not something that's typically done. But even that flexibility doesn't get away from hidden monopolies. So for this discussion, suppose I just said, okay, sure, we'll do that tomorrow. Still, I could give you a network that would satisfy this same problem.
So I'm missing something. Why you cannot bring 3 directly? Why do you need the capacity 1?
Kirchhoff's laws. So this is basically the consequence of Kirchhoff's law, that for every 1 you send here, a half has to go here. That's the line constraints. That's the way they bind. So that's killer. And this isn't like a toy thing. This, we have market power manipulation in terms of electricity prices, not this specific way, but lots of it. And, it didn't end with the electricity crisis. I got a nice settlement on my bill from this one in California, where they had to pay a lot of money for market power manipulation. And my favorite one is this, which was, I guess, last year at this point, 2 years ago at this point. So I love it. So they paid $650 million to buy basically the second largest generating plant in the Northeast, Brayton Point, and then they just shut it down. And this was a completely rational decision because by shutting it down, the network constraints bound in a way that they increased prices for the fleet that they already owned, and the calculations that I've seen, they made back this $650 million in less than a year. So, manipulations are possible, they happen, and the points, nothing that I've said so far has anything to do with uncertainty, but they're going to get worse with uncertainty. So Eilyan was talking about aggregators. So Solar City, I was talking over lunch with a few about this. Their big model is to install residential solar, and the view is to eventually pair it with their home energy storage. And now you have, as soon as that happens, you have 100,000 or more, basically distributed generators around large cities. And what can they do? Well, they're completely unverifiable. So you can curtail, you don't have to give your full capacity to the grid. You can decide when to plug into the grid, how much power to plug into the grid. And Solar City can do this, right? So the aggregators have the flexibility to decide when and where in the market they inject power. And they can do this to create price fluctuations. And so we have some initial work that shows that basically First of all, there's a great algorithmic problem, which is a nice optimization MPEG with robustness constraints saying, how would you do this if you're Solar City? And so if you're doing this, we have a sort of a nice reduction to dynamic programming, but there's some open work on just the algorithmic problem. It's a really beautiful problem. But suppose you can do that, and it's one with uncertainty, right? Because they might not know the network structure, they might not know the demand, so it's a great optimization under uncertainty. But suppose they can solve it. Then you can curtail less than 1% and raise revenue by more than 30%. And this is in realistic networks in Southern California and where Solar City actually has homes.
Curtailment means reduce.
Means reduce, so basically it means not put the full solar that's coming into the network. And this is without storage. This is just basically wasting the energy not putting into the network so that you create basically a need for electricity elsewhere in the network where you control it.
It's happening in the real-time market, right?
So this can't happen today in the way the markets are structured, but this is one of the ways, if this were to happen, it would be in the real-time market with locational prices exposed to the aggregators.
The real-time markets to be a little more upstream than it'd be harder to do this.
Possibly, yeah. But this is one of the things that really underlies how do you redesign markets to handle aggregators that have this kind of capability? How do you change a mechanism when uncertainty, and this is a place where uncertainty can hide basically coalitional behavior, right? You have a coalition in your network. Uncertainty hides the ability to observe what they're doing. Can a mechanism be robust to that? So it's a nice problem. But I want to get to the details of one way of going after these. So one very common way of approaching this problem and sort of seeing the complexity that the network creates is to look at networked Cornell. And I'll come back at the end. There's lots of problems with this model, but it's basically the best tractable model that the community has, although people like Eilyan and Kameshwar are pushing this. And so Cornell competition without a network is, I'm hoping everybody's seen at some point, but basically you have firms competing with quantities. So rather than setting a price, a firm decides how much to produce. And so in the two-firm version, just to warm up and get everybody familiar, you have two firms. They each decide their quantity. They have a cost. Think of things as, they have a cost for producing it. And then the price basically adjusts to clear the market. And how does that happen? It happens because there's a demand function. There's a function that says at this price, there will be this much demand. You know how much the firms are producing. So the inverse demand function sets the price of the market, and that's the price that the market will clear. Okay, and so you have demand, price, something decreasing like that. The inverse demand function evaluated at the produced quantities gives you the price. And that's your equilibrium. That's your notion. Okay, and then the goal for the firms is to maximize profit. So they basically choose the quantities that, given the price will emerge times the quantity they produce minus the cost of the production, is the maximum. So then that's the equilibrium condition. So the networked version is the same. And so this is the version, actually, this is from Kostas Pimkis and others that they presented at AC a couple years ago. I forgot to put that citation up there. But the network version is we have a bipartite graph. Think for now, don't think of these as constraints. They're just telling you 1 or 0 whether you can send to that market or not. So firms decide a total production quantity and how it is divided up among those markets. The cost is applied to their total production, but then the price is per market. And then they maximize their profit, which is given the price at the market and their total cost of production and how they divide it up among the markets. Okay, so it's exactly the same form, but you just have the sums to capture things properly. So that's that. And the key here is as long as the costs aren't linear, this isn't separable and it's more complicated than the single market case. And notice that this isn't even equivalent. If this is a complete graph, it's still not equivalent to the single market case. You'll still get different behavior because the markets are really separate in the way they function. Okay, so Kostas, when he presented this, basically was able to show existence. And then there's some follow-up work, actually simultaneous work, where they could look at the efficiency of computing equilibria in these sorts of markets. And that's kind of where it stands at this point. The only other thing so there's some nice results there on the computational side. There's lots of open questions about this model still, but maybe the nicest piece that you can pull out of there is there is some insight into market power that comes out of it. So you can characterize the equilibrium in the simple case of quadratic costs and linear inverse demand as being in terms of a matrix that I write here, which is basically a price impact matrix. It tells you it really tells you the price. So the marginals on this are the prices in the graph in the network. And so you can read out from that sort of a measure of market power. And I won't go into this because I'm low on time and I want to get to the electricity market version. But the key is that this matrix can kind of summarize how a firm that may not even be connected to the same markets as you impacts your prices. And so it can capture the idea that there could be a monopoly that doesn't even, for your market, that doesn't even produce for your market. Okay, so the electricity market version of networked competition is a little different though, because here we didn't have constraints on the network, and we just sort of, it was capturing who could send to what market. In the electricity market version, the network is the constraint, right? So the network, it's not a sort of matching, it's a which markets my production goes to depends on what other markets, or what other production happens elsewhere in the graph. And so there's this Kirchhoff's law, linear constraints on the market structure, and you have generators, or sorry, on the network structure, and you have the generators and loads distributed throughout the network. So it's a little different, but you can write it down the same way. And the other difference is this market maker. And so for the purposes of this talk, just think of the market maker as really optimizing social welfare. That's what they're regulated to do for the most part. There's a question of whether they should actually be doing that, but that's the regulations in most places. And so you end up with something where there's a market maker that's optimizing social welfare subject to the network constraints. And you have firms bidding quantities at different parts of the network, linear inverse demands at different parts of the network, and that captures your model. So that's it. So there's not, the only place where electricity really comes in here is the network constraints. And so, but actually all the theorems that you'll see in papers are typically for just general linear network constraints. Okay, and so the equilibrium is Cornell, which is the same as it was before, just in a slightly different language. And you can prove the same sorts of results. You can start to prove existence, and you can start to capture a little bit about the efficiency of these markets. But we really know not that much, I'd say. And so for existence, there's some interesting things that we can say. So it'll always exist under some of those ISO clearing mechanisms, but there are some natural clearing mechanisms. Like if you really wanted to focus on consumer surplus, and you had this, and California actually for a while was talking about maybe we should be really consumer-centric in how we regulate the grid and blah, blah, blah. Then you start to actually get problematic, and equilibrium don't always exist. And this is specifically because of market power manipulations. But if you're optimizing social welfare or residual social welfare, equilibrium will at least exist, which is a good first step. But that doesn't mean everything is good. So just to highlight how much this can matter, this is my caricature of California. There's basically large generators in the south, large generators in the north, and a few overcapacitated lines between them. And so the real line here, this is called path 15, and it really is kind of a big congestion point for the network in California. And so if we take this caricature, you can already see some interesting things. So if we had different clearing mechanisms for the ISO, you get very different behavior in these two scenarios. So you get basically, this is the case where an equilibrium doesn't exist under residual surplus. And what I'm pushing here is the capacity of this line. So notice that even in the uncapacitated lines, none of those three clearing mechanisms match what you would have with a single centralized market, which is this dotted line, although the social welfare is pretty close. This is just a fully connected network with no capacity constraint, and still it's very different from a single market, which is why it's so important to study these network markets. And then the other thing is these mechanisms really behave very differently. So if you imagine expanding the capacity of your network to try to help with efficiency, you'll have a very different impact with that expansion depending on how the clearing mechanism works. And we don't really understand this in general yet, but we understand it for some specific things. And so the big question underlying all of this is really, how do you design that market maker? Even if you are just trying to design it to optimize the social welfare, we don't know how to do that. Just to drive that home, so the natural thing, suppose I want to, if I'm the ISO for California, I want to optimize social welfare. That's what California legislature told me to do. So the naive thing to do is to set my clearing objective in that optimization problem to be the social welfare. That's what they do today. It seems natural and intuitive. That does not work. So that is unboundedly bad for social welfare compared to the optimal mechanism that you could use. What is the right thing? I don't know. And so, here's the unboundedly bad. So you can come up with examples that, setting the clearing mechanism to be social welfare has an unbounded P of A, price of anarchy. So unbounded efficiency loss compared to the optimal. And this is really scary in the sense that, Cornell is a simple model. If we had a single market, Ramesh has results from his thesis that basically say, efficiency loss is a factor of 3. 2-node network already is unbounded for Cornell. So the bad case here is that path 15 example that I showed you. I can already make things unboundedly inefficient. This is a bad example. And so what optimization, what objective would minimize price of anarchy is a clean, open question that we don't know the answer to. So I can say a little bit about it in the sense that we know, here's an extreme space, and we know that it should be sort of closer to producer surplus than the social welfare, but I have no idea, even if I wrote down just this space of parameterized clearing mechanisms, what the optimal would be. I can frame it as an SOS optimization problem, and for a specific case, compute it, numerically, but I don't know how to, really characterize what that is. But then I think, this is a nice, clean, concrete problem for network Cornell. But in the context of electricity, it's really not clear that Cornell is the right model even to begin with. Because at the beginning, I told you, what do you bid into the market? You bid supply functions. You say, I'm willing to produce this much for this price. And you bid this parameterized supply function. You're not bidding a quantity. Now, Cornell is a reasonable approximation in some situations of that, but bidding a supply function is a very different thing. And a natural question and a really important question is, what form of supply function should you bid? Because you can't build an arbitrary function. That's too complicated a bid space. So you need some parameterized class. What should that class look like? And basically, the answer to that is we don't know. Because almost nothing is known about models where you bid supply function in networked markets. There's a few papers. The nicest one is Wilson 08 if you're going to pick one to read on this topic. But just to give you an idea of what he can do, so this is a quote from the conclusion. If the conditions for equilibrium are so complicated as to impede academic and policy studies, then it's implausible to suppose that firms' bidding strategies approximate an equilibrium. So he basically threw up his hands at the end of the paper and said, we can't do it, nobody should do it, maybe we should look at different models, right? And that said, there's been some progress recently. Eilyan has a really nice paper looking at a simultaneous equilibrium model for supply function bids. Ermin Wei and her students have another paper that's just come out in recent years. So there's been some technical advances that let you start to make some progress in characterizing what an equilibrium might look like for situations when you're bidding a supply function. And so I think the time is right to be attacking those problems, and there's people here that could do it. But it's really a wide open area right now.
By the way, this figure is cost versus quantity. Is it the total quantity or it's a per unit? The price per unit or a total price?
You can think of it either way. So there are people that have suggested both. The reality is per unit. So the reality today is per unit.
Per
but
unit is always increasing.
Yes, yeah.
It's not a, like...
No, it's not that there's not a decreasing point. So right now, it's something that looks like that. And right now, they're piecewise linear bids in the real system. And usually 2 or 3 pieces is all that people bid. Okay, so is Cornell even the right model? And then notice that all of the problems that I just exposed don't really depend on uncertainty. And the interesting thing, and this is wide open, is suppose I throw an uncertain shock in. So suppose the generator that's bidding quantity has a portfolio that includes wind, so they don't actually know how much quantity they'll have available to them, and so that's impacting their price. 0 results about competition among wind providers in network Cornell. And then, connecting the 2 parts. This is now in the real time. This is happening after the long-term procurement. How does the long-term procurement, can we do a news vendor problem with network constraints? Again, completely open. Okay, And that's where I'll end. So, my goal was mainly to show you open problems and to highlight, news vendor problems. Multi-stage is crucial all over electricity markets, and that's something that we tend to not think too much about in the TCS, AGT type communities. And these network constraints and networked markets really being one of the fundamental challenges to the real time. And I think both of them are really rich spaces at this point where there's preliminary results, but nothing's closed off. And hopefully this motivates some of you at least to come talk to Eilyan and me and others about energy problems over the next couple months. Okay, that's it. Thanks.
Questions for Adam? Cool. Thanks for having me.